I just got this bottle of water through the TSA, and I feel like I'm going to be put on some kind of terror watch list. But thanks to some new technologies, this is actually becoming the new norm, and it's helping make airport security wait times much shorter. Thanks to these things, airport security scanners. Now, these may look like regular old scanners, but seasoned travelers have known to look for the lines with these machines for a few years, because they are much better than the old X-ray scanners. You know the ones where you have to take practically everything out of your carefully packed bags, or you get held up because some person in front of you, who apparently hasn't flown in 20 years, left their laptop in their bag. Well, that's about to change, but why? How are these newfangled machines making airport security less miserable and much safer? Both these and the new scanners use basically the same technology, X-rays. But these new scanners can somehow detect not only the shape of the things in your bag, but they are able to figure out what material it's made out of, which allows it to differentiate whether the liquid that's in your water bottle is water or some kind of explosive. Now, this confused the hell out of me when I first heard about it, because to the best of my knowledge, X-rays can't tell materials apart that accurately. I think most of us know how X-ray imaging works, but just in case some people in the audience don't, it works by sending beams of electromagnetic radiation through an object, and depending on the density and thickness of the material, it will absorb different amounts of the radiation, producing a grayscale image, with the brightness of pixels being determined by the level of absorption of the radiation. This allows them to identify things like knives or other metallic pointy things with ease. However, these older machines needed things like laptops to be removed, not because it couldn't identify a laptop, but because the dense materials of the laptop could be used to hide objects below it. This is where the first upgrade of these new scanners comes in. They are CT scanners, which are essentially 3D versions of X-ray scanners, with the X-ray emitter and detector rotating around the bags on a gantry, allowing it to form 3D images, allowing the security staff to look around your bag without having to pull out your laptop. I had no idea how this technology could be used to accurately differentiate between materials. How could these things detect explosives? A bottle of water and a bottle of hydrogen peroxide would look pretty much identical on a regular X-ray image. To tell them apart, the machine would need to be able to figure out the atomic makeup of the material with a decent degree of confidence, and do that quick enough that it can process thousands of bags a day with as few false positives as possible, while also dealing with all the other things crammed into your bag. This is far from a controlled laboratory setting. There are so many things that affect absorption, material density, thickness, and beam intensity. My curiosity was piqued. Every time I traveled through airport security, I found myself wondering how they worked. So I looked into it, purely for my own pleasure, but the answer was so interesting, I had to make a video about it. The first key to understanding this technology is understanding how X-rays get absorbed. The primary method is through the photoelectric effect. When electromagnetic radiation strikes an atom, some of that energy is absorbed and emitted as an electron. Denser materials have more atoms in a given volume, and so there is a greater chance of collisions between photons and atoms. The same principle applies for material thickness, with thicker materials requiring the photons to travel further through them, with more chances for collisions to occur. Just take a look at an image of a bone on an X-ray. Even though the center of the femur is the thickest part, it appears darker, meaning less radiation is absorbed. That's because the inner core of bones are not terribly dense compared to the compact outer shell. We need to eliminate thickness as a parameter, and the rotating gantry can do just that. It allows us to accurately measure the thickness of the material, allowing us to fill that variable into any future equation. The next part of absorption depends on the energy of the X-ray beam. Higher energy X-rays are less likely to be absorbed and can penetrate denser materials more effectively than lower energy X-rays. So, if we fired 2 levels of X-ray intensity at a single material, we could gain more information about the density of that material. Finally, and this is obviously the important one for identifying the exact material, is the atomic number of the material. Atoms with higher atomic numbers have a higher chance of absorbing a photon through the photoelectric effect, meaning an atom with more protons in its nucleus has a higher likelihood of absorbing the X-ray beams. If we can isolate just that variable, we can in theory estimate the material composition, and that's exactly what researchers did in this paper. They used a dual energy X-ray scanner, which allowed them to fire high energy and low energy X-rays at materials in their scanner. Then they could apply the absorption recorded into this equation. Remember we said we would need to know the thickness of the material to correct for that variable earlier? Look, there it is in this equation. This gives a new variable called mass attenuation. And by finding the ratio of the mass attenuation between the higher energy and lower energy beams, we get a new variable, and that ratio is directly correlated to the atomic number of the material. So we can apply it to a graph and begin classifying materials, and that's exactly what they did. I think I might love graphs and tables as much as Johnny Harris loves maps. Look at this table. This is the high energy absorption, and this is the low, and this is the ratio between them. We can identify water sitting at 7.42 with the researchers' estimated effective atomic number, Z. With this, we could have a computer algorithm automatically flag dangerous materials in bags and alert a security agent to open the bag for further inspection. And that's exactly what machines like these dual energy CT scanners of Smith's detection can do. But wait, there's a problem. Look at this table of explosive compounds. Well, there it is. They all sit at around the same value as water. Is this why we haven't been allowed to bring water through security this whole time? This is why. The error rate is just too high. Water is so close to all of these explosives that it triggers false positives, and false positives really slow things down at airport security. Most of us have been there, having the shame of our bag being automatically pushed to the naughty corner and having to wait for a security agent to rifle through our belongings to look for the bottle of water you forgot was in there. We don't like it, and airport management certainly don't either. It slows everything down and increases staffing costs. It's just easier to ban water and water-based liquids from passing through. So why are we now suddenly allowed to bring water through? What changed? That's an answer I couldn't track down easily, so I got on a call with an engineer from Smith Detection. I've kind of hit a dead end in my research, which is why we reached out to you I'm not quite sure how it can tell the difference between water and explosives, because in the papers I've seen, water is like 7.42 in their grading, and then like hydrogen peroxide or other explosives are like 7.3, 7.45, like they're all very bunched together. And that was my assumption, is that water was causing too many false positives, and that's why we haven't been allowed to bring water through airport security scanners. Is my assumptions right there?
So that was the start. So the atomic numbers were, the effective Zs were collected together, were grouped together, and if you fell within a certain band, you were classed as organic and given an orange colour. And if you were mixed materials and indistinct, then it was green, but if you were high effective Z, then you were given blue. So that was the start of it. The next stage was more than having a single view. You could have more than one view of a bag. You could have a side view, and you could have a top view or a bottom view. That starts to give you more data. That is the journey towards the other metric or the other characteristic we're measuring, which is density. So when you plot density in the Z effective, then you're starting to be able to discriminate materials much better than previously.
Okay, my research led me down the correct path, but the piece I was missing was that by taking multiple images of the objects inside the bag, the scanner has effectively built a 3D model of the item, and with that, it knows the volume of the item. Using this, along with the absorption data, the scanner can estimate the density of the material. This technology has actually been in use behind the scenes in airports to scan your checked-in bags for quite some time. The issue was making it small and reliable enough to operate in a practical security line, where getting people through as quick as possible is key. No one likes having to stand in a queue, and making that experience as easy as possible is good for business. Especially as the quicker you get passengers through, the more time they have to spend on overpriced beer on the other side. These things need to process bags quickly. They can't be breaking down constantly. They need to be easy and quick to service, and any false positives are going to force staff members to take your bag out of the system and manually check it, which is a pain in the ass for everyone involved and increases staff costs for the airport. And the next generation of security scanners are already being developed, using scattering and diffraction of X-rays, which is molecule-specific, to analyze materials. Right now, it's too slow for regular airport screening, but some are already in use in checked baggage halls. So, if you've learned anything from this video, next time you are in an airport, look for one of these machines. You don't have to take your laptop out, and if you are at the right airport, they may even let you take your water through too. Small, incremental engineering improvements like this may seem trivial in the grand scheme of things, but let's run some numbers. My local airport in Ireland, Shannon, is among the early adopters of this new policy. It's a relatively small airport, with 1.5 million passengers last year. But if this technology saved everyone going through security just 5 minutes, that's 9.75 million minutes saved per year. Or 18.5 years. That's a lot of time that people could be using for more valuable things. Small time-saving measures like this make us more productive as a society, and makes life easier for individuals. This is the power that a single inventive engineer can have on the world. We all strive to have impactful careers, and today's sponsor aims to help you find them. 80,000 Hours is a non-profit that aims to help you find a career that is both fulfilling and makes a big, positive difference. The name comes from the number of hours in an average career, 40 hours a week, 50 weeks a year, for 40 years. That's a lot of time that we should be striving to use to make as high a positive impact as possible. 80,000 Hours have done over 10 years of research alongside academics at Oxford University into how to find a fulfilling career that does a lot of good. And it turns out, the best way to make a positive difference might be pretty different from what you'd think. They also always try to avoid platitudes and unsupported generalizations. In fact, all their recommendations are based on careful research and consultation with experts in relevant fields. And when they aren't sure of something, they say so. If you care about what the evidence actually says about having a fulfilling and impactful career and want real advice, then 80,000 Hours can help. And everything they provide is free forever because they are a non-profit. Their only aim is to help solve global problems by helping people find the most impactful careers they can. If you join the newsletter now, you'll get a free copy of their in-depth career guide sent to your inbox. Just sign up at 80,000hours.org/real engineering.